Yes, then welcome to the first lecture in parallel and distributed computing in the summer term 2025. I'm going to record these lectures for everybody who's maybe coming later to this. So just that you know, when you don't want to be on the recording, don't talk too loudly. Yeah, but anyway, questions are always appreciated. So yes, this course will have a lot of practical parts, but we'll start today with mostly the definitions that we want to get out of the way. And now it depends on maybe everything that I'm telling you you're already familiar with, but we need to be sure that we have all these terms. So today it's kind of a little bit lexically, just getting the terms out of the way. Yeah, so a little bit. Okay, now I should start with something else. So there is plenty of resources online. So most people just go to Stack Overflow to learn programming, and maybe that's the better solution nowadays. There is for some of the theoretical parts we were using a book which is not necessarily a very recent book. Yeah, it's by Reuber und Rünger, Parallele und verteilte Programmierung. So this book exists in German and in English. The reason why I'm pointing out the German is because the German you can use with Springer Link. So when you're inside the network here, you can download the book in German. You cannot download the English version. Yeah? But you can, the book exists. I guess you can go to the library and get the hard copy of that book in English. Okay, so, and it's not necessarily a very new book because lots of things that we are discussing here is already known for several decades. Yeah, so maybe that's the reason why everybody is now running away and looking for other things. But even what is happening in graphics cards, yeah, from the principle. Now, when we talk about the principle, it's actually known for a very long time. Okay, and other than this, we'll go mostly about the terms. So let's start with this question why it's interesting to talk about parallel computing, and what things do you have to actually consider. So when I now can always say when I was your age, maybe a little younger, then computers were already, computers are always kind of getting faster. And to be honest, the dynamics, even though it appears that there's a lot of dynamic right now, but back then the dynamics was even more, you felt a lot of dynamics in the 90s, yeah? In what computer development was going on. But the idea back then was different. So we usually had all serial computers, and the way the serial computers got faster and faster and faster was by increasing the clock rate. Yeah, something that is completely. So everybody was talking about. I even remember the time when I said, so this computer has that many colors and that computer has that many colors. So suddenly nobody talks about colors. Yeah, then and then there's memory and clock rate, but mostly clock rate. So clock rate is something nobody talks about today. Yeah, 20, 30 years ago, it was all about clock rate. You see, there is things are getting faster and faster, but not everything is getting faster in the same way. So I got somewhere some numbers. That this is very unscientific because I don't remember where I got them from. And they may be wrong, but they are not very wrong. So you can measure the increase of compute power. And usually what we observe from, you've certainly heard about Moore's law, right?
Yeah.
And do you know that this is actually first Moore's law? Do you know what the second Moore's law is? No, okay, I see. So I'm actually a hardware guy. So I learned. Konstantin, do you know what second Moore's law?
Yeah. Moore's law.
The second one.
Second one. Yes, second one.
No, the second because that's what comes from an Intel guy. So the first Moore's law is the number of of transistors on a die increase double every 18 years. Yeah. The second Moore's law is I don't know the number exactly, but this is the cost of a factory for building semiconductors doubles every roughly the same time. Yeah. So this obviously has some very important consequences because if you the cutting edge semiconductor production factories in the world, or not the factories, maybe the companies that build semiconductors, cutting edge semiconductors, have always been and will always be in the single digits. Yes, so second, this is not what I wanted to talk about, but okay, I'm telling, so all these things in rising, putting up the compute power, these things still increase exponentially. So they grow by a constant factor each year. Yeah, and so like obviously the first Moore's law, that the number of transistors on a die, they will double every 18 months. So, and when you translate this into operations, then what you see is that you get integer operations. So because they increase exponentially, you can give a percentage. Yeah, you can say they are in 1 year 55% per annum. So this means they are now 55% faster than they were last year. And in 1 year, if world economy does not do this now, yeah, they will be 55% faster next year on kind of long-term average. Yeah, I mean, this of course goes in steps, because every time they have a new architecture stuff of like things. But in the long term, this is the observation. So, what is growing faster is because this is important for doing interesting things, like whatever you consider interesting. Nowadays, it's deep learning and artificial intelligence. This, for example, needs this. So they need floating point operations, and this grows 55% per annum. Yeah? So this is faster than the integer. So, I mean, so when I'm old guy thinking back, yeah, integer operation, so the gap between integer and floating point operations was much larger than it is today. So, I mean, like, doing floating point operations on the computers in the 90s was very, very slow. Yeah. So actually they had to write, each floating point operation was a program. Yeah. So there was no hardware for floating point operations. This came with the I believe with the 486, I think, that they introduced, Intel introduced floating point operations in the x86 architecture. So, another thing, memory capacity by 60% per annum. By the way, now I'm confused because we started late. When did we start? Like quarter past? I don't know. So when I don't know when to start, then I don't know when to finish. I just go on. So, okay, memory capacity, you see, memory capacity grows more slowly than floating point operation. Yeah? And now actually comes the trouble, because you could say they are in a similar range, these things. So they grow differently, but they don't grow drastically differently. But there is one thing that grows drastically slower, and this is memory access speed. And this only grows by 25% per annum. Okay? And this is actually more or less what is defining now the evolution of computers, and how scientific computing and computing in general is changing over time. Yeah? Because the efficiency considerations in computers completely change from so when I was young, memory access was something that was absolutely not considered at all. This is, you would consider this to be instantaneous, yeah? And floating point operations would be very expensive. Now, per annum, so going on 20, 30 years, you see, this has completely put upside down, yeah? So now floating point operations are basically for free. And reading something from memory is extremely expensive compared to the floating point operations. And again, 30 years ago, this was completely the opposite. And because these things are going on, I mean, it is not the thing that somebody invested their money in the wrong things. There are physical reasons for this, and if you look physically on how a GPU is built nowadays, you'll see that they put memory access to the absolute physical limit. Yeah. Okay, so this actually has this actually has a name. So this is the data starvation crisis. So back in the day, we called this the memory wall. So they said that we can make computer faster and faster and faster, but wait. We have this memory problem. This is a theoretical problem. And actually now we are now inside the wall and try to, dig our way out. I'm kind of making this stupid cartoon characters. Never mind. So the compute capacity grows much faster than memory access speed. Meaning that whatever you do, your time to solution is governed by how fast you can access the memory. So, always increasingly. I mean, one thing that you observe nowadays is that the way you solve problems is changing. You may use different algorithms nowadays that would be considered, I mean, different compute architectures, but also different algorithms to solve a problem nowadays that would be considered inefficient in older times, yeah, but now it's becoming more and more efficient. Yeah, so you see, they're shifting from doing it that way to doing it that way, and at the time of the saying, you basically observe that apparently almost everything is going toward neural networks. Neural networks is not a new concept. We know this for 60 years, yeah, how this works, but that we are using them in that extent that we are using them now is a new thing. And neural networks have the advantage of being very, very parallel, so that they are actually, in a sense, they are extremely inefficient in what amount of energy they eat, yeah. But the good thing is you can put them in parallel. You can do they would do almost everything in parallel, and so you can make it relatively fast compared to other serial methods that would then use much less floating point operations. But because floating point operations, you don't care, yeah. I mean, it's not the only it's not the only thing why neural networks are now coming up, but this is one of them. Okay, so what we observe is when we build new hardware, and now also when we here will not build new hardware, but we have to care of what hardware is being built in order to use them appropriately. So the hardware of the parallel machines and their evolutions, they have to take the data starvation crisis into account. And they do. Okay, the way we do, we'll see probably a little bit in further lectures. Let us first come to the machine classification. According to Flynn. So even though everything is dynamic, the dynamic is relatively constant. Yeah. So let's say the concepts and how things will evolve was already known quite long ago. So this classification is actually from 1972. This is even older than me. And it was in Transactions on Computers, C21, number 9, and it was in 1972. Okay, so what did Flynn classify? So he's distinguishing 4 different types how you could build a digital computer. The first is they are not pronounced the way they are written. Yeah, so I think this is called SISD. Yeah, it's not SISD. It's called SISD, and SISD is the concept of a single instruction, single data. Okay, simple sequential computer. Then there is MISTY. Okay, do we pronounce this MISTY? Potentially. So in German, Mist is, okay, in English mist sounds like fog, yeah, but in German, mist is manure, right? So it's this kind of computer is, I could say in German we could say this is mist. This is mist computer. So very sorry for this. Stupid, childish. It's multiple instruction, single data. This is something that is difficult to find in the real world. Then there's SIMD, single instruction. Multiple data. Now these guys are completely on the rise because this is where neural networks live. And then there is MIMD, so this is what you have in your laptop. Multiple instruction, multiple data. Okay, let's look at these guys in general. So SISD. So this is the classical one-core computer, single core. Machine, so such things die out. So your smartphone and whatever has at least 4 cores, I guess, or even more. So I think they are not going to die out. They will usually be in your maybe your fridge or your washing machine will have something like this. Yeah. So here you have a completely sequential programming. So this machine is not parallel. You could argue that there is something in these machines already that is, or could be in that machine. There is pipelining. We will not talk about pipelining, but pipelining is something that where some of the sequential operations could be done in parallel. Yeah, but pipelining was, I guess, not invented in the 70s. So we have, it was not common. I think it was not common. So how does this work? We have data. We have a processor. So they interact, and there is one program that tells the processor what to do with the data. I mean, the program kind of also is data, but they are kept they live in the same memory, but they are kept separate, yeah, in separate parts of the same memory. Okay, so this is the classical computer. Then the one MISD. So what is actually this doing? So you have data. You have one set of data, and you have multitudes. You have multitudes of processors. There you have processor 1, and then you have many, and then you come to processor n. So there can be any number of them, and each of them is run by a different program, but they work on the same input. I know only one example where this has actually been implemented. So what do you think is this good for? Seems to be a difficult question. So, because they are using the same data, yeah. Basically, I mean, the idea is you get the same input and you write the same output. So how can you write the same output if there are different programs? So basically, they all need, because there's only one memory in data, so they would write to the same output. So then the only way where you use this is to see whether two independent programs, I mean, they are different programs, but they should give from the same input the same output. And the only reason why you would do this is to actually see whether they agree or disagree, right? So, for example, if you have something that cannot go wrong under no circumstances, then what you can do is, or what in engineering you do, you use redundancy. Yeah, so you take the same part several times. But wait, do you take the same part several times? Because now obviously if you take the same computer running the same program, yeah, then or any other physical object, the same thing, then you're always in the trouble that they can fail for the same reason. So the Fukushima power plant had 13 diesel generators that would keep the the ventilation running. Yeah, so they were all the same, and then there were this one wave, and then they were all gone. Right? That's so. What instead? So how do you get around this? You could have different concepts. You can have a diesel generator and you have good batteries. So there is a possibility that when the diesel generators are overrun by the wave, the batteries may still work, right? So extending this to parallel programming, what you could do is you let you have one task, you give this to one guy and to another guy, and they write their program, and then they run in parallel, and then you see whether they agree, right? The question, of course, is what you do when they don't agree. So one way you could do this, you have not two, but you have 5, and then you do a majority vote. Yeah, so this is one way that could be done. So if if one of this program has a programming error, then the other may not have this programming error. Not the same, right? This is the hope, but it's not commonly done, and it's also questionable whether this actually improves reliability. I mean, this machine is not common. So application is obviously fault tolerance. And this is what we call functional redundancy. So it's redundant, but it's not redundant that you have the same thing several times, but you do something else that should give you the same result. And this was implemented in the space shuttle. But I don't know anywhere else. So, okay, so this is something that we'll not talk about in this lecture. SIMD. So, single instruction, multiple data. So what you get data 1, to data n, and you have different processors. The 1, and you have n dot. But they all run the same program. There's only one program running all of them. And this is what we call the vector architecture. So actually, this kind of thing was relatively popular very early on, like I think even in the 60s or 70s, so it was very popular. And then it kind of disappeared a little bit, and then with GPU and artificial intelligence, this you could say artificial intelligence lives here. So they become now much more common than they used to be. So in between, in the years in between, there was a little bit the idea that this is a bit inflexible because they always run one program. So there is the one that is most flexible is multiple instruction, multiple data, which basically looks a bit like completely separate computers doing completely separate jobs, but they also have the opportunity to work with each other. So these guys have their own data, their own processor, and their own program, so they can work completely independently. And this, of course, looks like it's the most, this is the most flexible, but it's not necessarily the most efficient, because this is also the most heavyweight. So you have to invest the most here. So depending on what you are doing, but this is where your laptop PC is. So this is multi. This is in particular good for multitasking. So when I do like this, I'm writing my lecture and I have a recording of my lecture running there, and so my computer is, and then there is a virus scan going on in the background. So this kind of architecture is what is in your personal computer, because you're doing independent tasks at the same time. So let's let us come to all of the definitions. I'm hoping I'm not boring you too much, but we have to get these guys out of the way. Yeah, that we know what we are talking about. So we will here, and Konstantin did this in the beginning. We'll talk about, for example, cores. And what we mean by a core is an arithmetic unit plus, so this is not a T, this is a plus the control unit, control with one L, I believe, control unit. They are conducting the floating point and integer operations, also the control operations, which are usually integer operations. So this is something that you cannot split up any further. Yeah. So in the old days, a core and a CPU would be the same thing. Nowadays, this is different. Yeah. So we have the central processing unit, which originally was one core. Now this is a thing that contains usually many cores. And this is now your main processing unit in a computer. It's also commanding everything. Yeah, so it runs also the operating system. So your graphics card, even if it's much faster than your CPU, is not running the operating system. It always needs the CPU to get told what it's supposed to do, right? So this is why this is the main and central. So without this, there is no life in your machine. So typically nowadays it contains several cores and caches. So I guess most of the terms that we are talking about are well known, but anyway, we'll have to introduce them. Cache. A cache is a fast indexed. That means there is a fast indexed memory, meaning that that together with the data, there is actually the location stored where it would be, because this is not the entire memory, but there's a memory that keeps selected copies of the main memory. So I guess this is something that you know. You will also know what RAM means. Yeah, do you still know what a ROM means? You still need ROM. What is ROM? Read-only memory. Yeah, you need a bootstrap, right? So it has to start from something. So random access memory. What you see here is that this is an old name. Because if you would invent the same thing again, you would not call this random access memory. Because the point with random access memory is that you imply that you can read from any place and it always takes the same time. Now, what I told you about the starvation crisis, this was true 30 years ago. It's no longer true today. Yeah. So random access memory is what we call the main memory of a computer. And then we have a bus, and nobody I know actually know what bus stands for. It stands for something, but you know the thing that is called bus makes it so it's just the thing that carries everybody around, right? Bus is and it's even it's even a theory that it does not mean anything. But okay, it's a data transfer system. So we have several buses. So it could be between RAM and CPU, for example. Can also be in a network. And this typically consists of several lines. Not always. So there's so-called, what is this? Serial bus. A serial bus has only one line. Things come in sequence. So, okay, I guess all of this is known, but we need to introduce this so that there's no confusion about what is coming next, namely the bus width. Yeah, which is also something simple, but we have to distinguish it from other things. So this is the number of parallel lines in a bus. So usually the number of lines in a bus defines also the size of the chunk that you are moving around. Yeah, so you cannot in a serial bus you can in principle transfer a single bit, but with a parallel bus you can only transfer pieces. Yeah, they always come together, and this bus width has to be distinguished from the band width. The bus width is the number of lines, and band width is the data throughput. It's the rate of a bus or network, so any resource that transfers data per time. So here you don't care how many of these lines come in parallel, but only you measure, so what amount of time does it take to actually arrive. And this is, for example, then given in bytes per second, yeah, or in whatever, gigabytes per second, yeah. Okay. Then comes the latency. So latency is the response time of a bus or network that means the time between query, so you're asking for something, and start. Okay, so this is important. When your data starts to arrive. So here you have to make a clear distinction between the bandwidth, so how fast is, how much data is transferred per time, and the latency, how quickly it is going to arrive. So what you measure in the bandwidth is you have a very long stream of data, yeah, and so how much data comes in per time. So this does not take into account the. I mean, you could see this as a kind of a river, yeah. Obviously, it's a stream. So you see there is a place where you can pull a lever and then water is going on in the stream, yeah. And once you've pulled the lever, then you will have 1 million liters per second coming down. But if you stand very far downstream of this and you tell somebody open this lever, then you have to wait an hour before anything comes. So this is the latency, yeah, before something starts to arrive, and then later you see how much is coming per time. So these things have to be distinguished. Both behave in a different way. So then also we have to distinguish between different kinds of memory. For example, shared memory and shared memory is the one that is accessible from the participating cores. So it's shared between cores. Which we have to distinguish from distributed memory. Which is then only accessible from the associated cores. So this is like other things in the family, you know, memory can be shared among several cores, but be distributed between others. Yeah. So maybe I guess I'll draw this later again, but as an intro now, say we have here several cores inside the CPU, and they have some RAM. Here. So, and they say there's network. And then you have the same thing again. So you have a core, several cores inside the CPU. You can also have several CPUs there. And then you have this RAM here. So you see that you could say that inside this here, this would be shared between these cores, but it would be distributed among these what we call nodes. Yeah? So because we'll call this here processing node 1, and this is processing . node 2, and I just noticed I did not introduce processing nodes. Processing node is the unit of one or more cores with shared memory. So the unit where you have the memory shared, we call this then a node, yeah, in our network. And for example, in the Phoenix network and the Phoenix network, the Phoenix cluster. So a cluster is, I think combination is probably not the best word, but this is the one that I came up with here. So it's some sort of combination of several compute nodes. So this may be a high performance cluster, or it may be here, the computers on your desk that are somehow connected over the internet, yeah? A little bit, because they stand next to each other, they would be connected a little bit closer than the internet, but you could use the internet as a network, which should not do in high performance computing usually, because it's very slow. So, what else? We have the so-called compute power. Okay, don't run away just because today we get all these terms. This may be a bit, I guess this can be a little bit boring now, but we have to get them out of the way, yeah. So we'll not do terms all along. We are not here in law or something. We'll do programming later, yeah. So the compute power of a machine is the maximal number. You usually don't reach them. The maximum number of floating point operations. So you see this definition does not take data starvation into account. Yeah, you can have a computer that on the paper is very fast and in practice is very slow. Yeah, maximum number of floating point operations per second. So this is a bit unfortunate that it's written like this. So actually I always believe you should write it like this. Yeah, so this is per second. Yeah, floating point operations per second. So floating point operations, and also, what is a floating point operation? This is also a problem. So obviously a multiplication of floating point numbers is a floating point operation. And addition. So these are, multiplication is a cheap floating point operation, yeah? It's much cheaper than taking a square root, but the square root is also floating point operation. So most of the time, taking a square root will take more time. So if you measure maximal floating point operations, you take the simplest operation that you find in your machine, yeah? And there's another problem that I have to admit, I don't actually quite know how they cheat with their numbers in respect of this, but what modern computers can do they can use triple operations where they combine additions and multiplications. So if you sum up two numbers and you multiply by something, this is something that they can merge in one operation, and then it's it's twice as fast. No? Now I mean that it can do this also means it's not necessary. I mean, if you just count the number of operation, the number of plus, minus, and multiplication signs in your code doesn't really tell you how many operations it is doing, because it may merge some of them. So then, as I just said, there are other things that may actually be implemented on your hardware, like division. Division is obviously implemented on your hardware. The square root may also be implemented on your hardware. And other things, they are more expensive. They usually use more than one clock cycle. Multiplications and additions and subtractions are the cheap one. So, more terms, a thread. So, I always try to find a better definition of a thread, but I don't really get to something that's really nice. So I wrote down as an independently executed sequence of instructions. The thing here, and this is why it's called a thread, like a thread that you put with a needle through your clothes, yeah, to do in sewing. They are always sequential. So the thread is the sequential line of doing things, but they are also from a computer, from execution perspective, this usually deals with its own data, and it also has its own place in the program. So it has its own program counter, yeah, compared to the others, which when you come to vector machines, again, you have to be careful, because you have a machine with many threads that go together, yeah. So they are at the same location in the program. And yeah, okay, but I hope you are kind of a little bit familiar what these things mean. Then you have a process or task. That's the instance of an application that would usually have at least one thread. Okay, to get a little bit away from all these, we are just giving names here. Let's look at threads and how they executed in single instruction, multiple data. Yeah. Say we have this program. So say there is if, and then you have a query. So if Q, right? So if Q, then do A, and else do B. Yeah? Say we have this kind of program. And let's talk about this vector machine where we have several threads going the same way. Because the question is, can you actually, on a vector machine, do different things? And indeed, you can make them do different things. Like you would have here in this, you have one program, yeah, but depending on what Q is in the different threads, they would execute different parts here, right? So how is this done? Say we have thread 1, thread 2, and thread 3. Yeah? And say they run here, so this is their time. And now let's say we have this program here where we have the query, so if Q, right? So now assume this will give us true here. Okay, this is very stupid to write true. Okay, let's say this is green. So this is true, and this is false. And this is again false. Okay, this is possible, right? So, but now they have to go on and do, the program, because they can execute only one program. Yeah, so they would now do A. So what is now happening in reality is that there where we have true here, this will execute, and the others will be dormant. Yeah, so they just do nothing. So there is in vector machines, there is a possibility, so the thread cannot do anything else in that time, because there's only one program counter, but it can be turned dormant for some time. Okay? So that means the others are dormant. So how do I, okay, I should have taken a different color here. So they will be, yes, so they will execute, and the other ones, they will not execute. So say this is, okay, no. Say it is, we call this, no. Yeah, so they sleep. Okay? So then comes do B. Do B or not to be, what nonsense am I saying? So these things, they execute, and this does not execute. This is dormant. So saying that okay, so you need to be aware of this when you write your program. Because first of all, the most important thing is to know that using vector operations, you can actually do conditional statements, so you can do some sort of branching in principle. But the branches will be sequentialized, right? So you should use branching very sparely, right? Because if you put this one into another, they will all be flattened out. Yeah? So this is important to know. So then compared to this, okay, now yes, I just wanted to mention the obvious. So okay, let's write it down, why not? So in SIMD, so it's not in SIMD, we still have threads, but these threads have, we could have given these things a different name, but this is the name we still use the name threads. They have independent data, so Q can be true for one but false for the other, but the same instructions, and they will be put into sequential format. So this is of course different from MIMD. So in principle, in MIMD, threads could do completely different things. So there is no reason why they should run the same program in the first place. However, often this is what we still do. We have one program and run it on the different. We still run the same program in principle. Yeah. So let's consider this you have the case where one thread is running your web browser and the other one is doing something completely different. Then they don't care about each other. But here, let's say they have independent data, and the instructions are also independent. I should read before I write. Okay, so independent data and independent instructions, but you can still run the same program. So you can run either the same or different. So if you would like to make a similar picture to what we had above, then you would have thread number 1, thread number 2, and thread number 3, and now the assumption is that they run the same program in principle. Then we'll have time here. Now the thing is, while I was writing the program up here, sequentially, this is not actually what I can do here, because they may come to doing the same thing at different times. So say this is if Q, and say this is true, and here is if Q, this is true, and I did a little bit further. Okay, now the other were full. Let's do it full. Okay. So they don't need to be in sync. So they could come here, and this one can actually be before this if Q also false. So what this thing here would now do is it would do A, so this would do B, and this would do B. Yeah, so independently, in parallel. Okay, pretty simple. Don't fall asleep. Memory access. Okay, again, shared and distributed memory. So this is very important, and so far it's not so very well. Evolution of hardware makes it more complicated than it used to be, because what is shared and what is common, this is again kind of getting a little bit blurred nowadays. Yeah. So we have, say, we have our processor, we have another processor, and they are attached to the same bus, and they go to the same RAM, and this is what is classically being the shared memory, because both processors go to the same RAM over the same way, and therefore they will have also it's as difficult for either of them to arrive on the same location. So, and when you have a machine that roughly looks like this, and you don't have machines that look like this, yeah, so hardware is actually different, but if you have a machine that more or less looks like this, then the way you would do your programming is you use shared variables. So, I mean, you do parallel programming not because you have completely independent tasks that you want to do. Sometimes you also have this, but usually you want to solve a problem that requires some interaction. Yeah? And the way you let them interact is that one writes something into a variable, and then the next time the other one reads this. This is this shared variables thing. Now I'm using Laplace here as giving some advice or some warning. Now, if you do this, then you have to keep track who was the one who changed the thing the last time. Yeah. And in particular, accessing the same variable from different threads is not allowed. So this can lead to non-deterministic behavior. If you try to do this. Now distributed memory. I mean, shared memory is a thing where life is easy peasy. Distributed memory makes life more complicated. So this means you have processor, could be several processors with their own RAM, processor and RAM, and then they talk on a network. So, and then this means that each machine can only access their own memory. Yeah? And here you would do your programming in a completely different way. Namely, you would use message passing. Okay, so depending on whether you are in a shared, so this is the first the first thing you have to, okay, the two things that you have to distinguish in parallel programming. First thing is you have single instruction, multiple data, or multiple instruction, multiple data. So this divides the concept. And the other thing is you have shared memory or you have distributed memory. So these are the two main dimensions that you have to keep in mind, yeah, to make a decision on how you write your program. So, life is a bit more complicated than this actually, because there are several buses, several caches, and several things going on that memory is not as accessible from everywhere. And also for this, there's some nomenclature which is probably now not so mainstream anymore, so you can wake up. So there's UMA machine. I mean, this is a Platonic concept, if you will. This is the uniform memory access. And I guess in principle, I mean, this is the type of computers where where I grew up with, and yeah, more or less there were other problems back then. But this is where the concept of random access memory also kinds of comes from. But yeah, a UMA machine, a parallel UMA machine, implies that all the memory access takes the same time, regardless of from where, yeah, or from which processor or core. So this is usually nowadays no longer true. Therefore, there is something that is not UMA, and this is then called NUMA. As for non-UMA, this is non-uniform memory access, and this means the access time depends on the location on memory. Okay, for example, what you have to know is then, since shared memory programming is so much easier than distributed memory programming, it's more convenient to use the functionality of shared memory. And so what you'll read in some specifications is that, for example, in this graphics card, blah, 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 now with this compute capability offers a virtual shared memory, right? So that means you can access, for example, when you hear about a graphics card that it uses virtual shared memory, then you can write from the programmer's perspective directly from the CPU into the memory of the GPU. And now, of course, it depends how efficiently they implemented this. But, you know, the memory of the GPU is not physically connected directly to the CPU. And the other way around too. I mean, mostly the GPU cares about that they can read the memory of the main memory directly. And they have some hardware components that accelerates this. But physically, there is a price to pay, because the memory that is built on the GPU is physically closer to the GPU than the memory in the computer. So they will always this virtual shared memory always comes with a lot of overhead. Yeah. So because I mean this is all related to the physical distance. So already I remember one thing that my electronics professors told me. There's what we call a light foot. So a light foot is 1 nanosecond, because 1 nanosecond is the physically event horizon. So one foot is the physical event horizons within 1 nanosecond, because the light travels 1 foot, so 30 centimeters, in 1 nanosecond. Why is this important? Because your computer usually has a clock frequency of roughly 1 gigahertz, 2 gigahertz, something. So bus will have roughly 1 gigahertz, clock rate. This means the event horizon within that frequency is 30 centimeters. If a memory chip, I mean, you see how big the computers are, so they are less than that. But if a memory chip would be, I mean, they have to go twice the distance, query and answer, yeah? So if a memory chip is further than 30 centimeters away from the processor, it cannot be accessed within this 1 gigahertz framework, yeah? So, and this is why you usually have this the problem that the location of your memory defines, I mean, physically, yeah, physically limits your timing here, yeah. So, and this is of course, I mean, this is of course the more I mean the way the hardware is implemented actually is, I mean, the physics defines how hardware can actually be implemented, and then it also is somehow implemented, and the way things are implemented, and I'm still drastically simplifying things. Yeah, so you have a CPU on which you have several cores, and I now simplify things by writing that there is one cache, which is also not true. So there's usually at least 3 levels of cache, and 2 of them will be associated with one core, and the third one will be associated with the CPU. So that they have caches that they share and caches that they don't share. Yeah? So, but they always have caches that they share, and now the thing is, you don't have only one CPU necessarily. So you would have one CPU in your mobile phone with several cores. But you'll in a high performance computer, you will have also several CPUs within one compute node, right? So they would then work like this. So there's several CPU with several cores each. So for example, that would be in the cluster that we are using, there would be two CPUs with 10 cores each, right? Nowadays, there are even more than that. And then what you could do, what you could have So this is one possibility of a setup, that both are connected to the same bus. And when they are connected to the same bus, they can both access the RAM with the same speed, say, yeah? So, but this is usually not the way hardware is implemented. The way hardware is implemented is more like this. You have a CPU, and now this is for example again the way the Phoenix cluster is, for example, implemented. So here with the simplification that they only write the level 3 cache. So there's one CPU here, and this CPU has a bus. And this bus is not connected. So this bus has its own, the bus connects to the RAM of that CPU. And then there is the other CPU, or the 4 others, or how many there would be, with their own number of cores that are connected with their caches, and they have a bus too, and they connect to the RAM. So now this is still shared memory because it's in one node. And the way they share the memory is because these CPUs are built to live together. What they have is a so-called bridge. So the CPU of the one CPU, so each CPU has their own RAM, but they have a bridge to the other CPU, and they can bypass, so they don't need to ask the other CPU to give them their data, to send them their data, but they have a bridge where they can bypass the CPU and go into the bus of the other CPU. But physically, they have to go over the bridge and then take the bus. So this physically means that there is a range. So for each processor, there's a range of memory that they can access more quickly than the other. Yeah, because the other is the memory of the other processor, which they can access through this bridge. And this bridge, so in high performance computer, so this is also why these things are more expensive than the stuff that you have in these consumer computers. So they have a very broad bridge. So they want to have the possibility that they access that they go over the bridge as quickly as possible, so that the delay is very short. But you have this delay. Okay, so this okay, I didn't write any. Okay, I give the explanation, hopefully. So a few more before we come to an end here. There is cache coherent NUMA that we call CC NUMA. And in this, the data inside the cache is kept valid when accessed by different cores. So this again is this you can implement, but this is kind of expensive. So the idea is the following, yeah? So because we are inside the memory wall, so what we do against the memory wall is that we copy chunks, actually pretty big chunks of our memory inside the CPU, inside the caches, and work inside the caches. In parallel programming, in shared memory parallel programming, this obviously gives us the trouble that when you want the work that your colleague has been doing, your colleague has to return this somehow to the main memory before you can access this, because this is now in the cache of your colleague. Yeah? So, and in particular, you don't know whether it has been returned. So what the cache coherent NUMA does is, when something is changed in the cache, or if something is taken to the cache, it has to make a note somewhere. So there is yet another part of memory that keeps track of saying, so this line in the memory is dirty. Yeah? So either you don't touch it, or when you touch it, we have to return it. So that means so this can be implemented in different ways, and I actually don't really know how it's usually implemented, but the thing is, if one processor is changing something in their cache, yeah, they need to make sure that if the same memory is in the cache of another core, that this is sent to these other cores so that these caches are synced. And this is, of course, important, and because it is important, what did I say? It's expensive. It's expensive, and because it's expensive, you can also have a different, you can also always put everything on the user and say there is non-coherent NUMA. So here you are actually in the trouble that the caches are not kept synced, and that you yourself have to make sure that you know whether the data has been updated or not. Okay, kind of last point. So we are talking about this because the performance of your program, so you need to know how your machine works in order to efficiently use it, right? The problem is that we have this theory, but we also have commercial machines, obviously, that are also changing with time. And even though I kind of learned this 20 years ago, when there's a processor coming out, I cannot tell you how these things are implemented because they don't tell me. Yeah. So this is you can measure performance. Yeah? This is usually what we do. Yeah. So this also we'll talk about this. Because you may have the wrong you also may have the wrong idea on how your machine actually works, because there's a lot of detail now. Yeah, there is billions of transistors on this die, so you as a programmer don't actually know exactly how things are implemented there, and you also don't want to care, but you should also not completely ignore it, otherwise you get a bad performance. Yeah. So one thing that we that is pretty standard is, for example, due to the buses that have a certain width, and they also become wider with sometimes, so 60, I mean, and they may have, several 64 bytes to 128 bytes, yeah, so, and so they read lines into their cache. Wait. So, for example, then if you read memory, then you would always read this in cache lines, because we make copies into the cache and they are of fixed length. Now there's a lot of detail to know where the cache line starts, how long the cache line is, and so on and so on. But one relatively simple thing to know is that cache lines are always sequentially. So memory is one-dimensional. You get a chunk of memory that is copied into your machine, right? And this already gives you a clear reason to also process your data in a certain way. For example, say we have this two for loops here. So say for int I is equal to 0. By the way, we are using C++ here in this lecture. So I'll always use also C, nomenclature. Yes, style here. So say we have two of them in each other. So J is smaller than Ly J plus plus. And then we have, say, date 1, and I'm now writing to something, but I'm also, we also write. So we are reading cache lines and we're also writing cache lines. Yeah. So say I'm writing data 1 I plus Lx. So the length of, say, we have one-dimensionalized our data. Yeah. So I write data 1 I plus Lx times j is some function of I and j, say. And then I write date 2 is j plus ly times I, and say this is the same function or something else, doesn't matter, I and j. So here you should probably not do it this way, because this would always give the same result, right? But this is not my point. My point is, you see, so this is not a parallel program, obviously, yeah. So it's sequentialized, yeah. Now you are doing things in a certain order, and you could also do things in a different order, usually, because they don't depend on each other. And now the question is, which is a good order and which is a bad order? Yeah. So they do, the two of them have different orders. So what you do in data 1 is you have an inner loop, this j, that is the one that is faster. So you go through all of the j while you're keeping I the same, right? Whereas here, so what you're doing here is you're going in steps of Lx, right? And here you are going in steps of 1. So in the data 2, you're going sequentially through your data. This means as long as you are within the length of one cache line, yeah, so you will access so the first element of a cache line, and the second and the third, and so on. Yeah. So the entire cache line in this operation has to be written only once, right? Whereas if Lx is longer than one cache line, now it becomes, because of the size of caches in modern processors, you would have to have a lot of data, because in this case, they would write the cache lines in several lines, and because they have a lot of cache, you would keep many of these lines simultaneously inside the cache. Yeah, but say you really have a lot of data, then this here is a trouble, because if Lx is larger than one cache line, you'll never write data sequentially. So you always have to clear the line, and this may be very inefficient, while this, because it actually uses the cache, may be the more efficient way of doing stuff. Okay? So, and this, in principle, was the first theorization of this. So what we do next time is we talk a little about on the theory of networks, and a little bit of theory of modeling of parallel programming, and then we'll come later to the actual exercises, in particular using MPI. Having said this, okay, I'm closing so because organization is not important for the recording.